our first two speakers are ready to go. Gentlemen, all yours.
Okay, so hello everyone. Thank you all for having us here, and thank you for coming to our talk. It's a real honor to start the event. Today we're going to talk about scaling runtime application security, how eBPF is solving a decade-long challenge. But first, let us introduce ourselves. Sorry. All right. So my name is Guy Kaplan. With me is Avi Lumelsky. Let's Avi introduce himself.
Yes, so thank you guys for being here so early. My name is Avi Lumelsky. I have 10 years of experience in R&D. I focus mainly on AI engineering and security research. And I also really love to climb mountains. So if you're into hiking or mountaineering, we can climb a mountain together. And with me is Guy.
Okay, so I'm Guy Kaplan. I'm a vulnerability research lead at the CTO office of Oligo Security. I have more than a decade of experience with vulnerability research and software development. And in my free time, I'm also a scuba instructor. So let's dive in. So a bit about what we're going to cover here today. So we're going to talk about RASP, or Runtime Application Self Protection. We're going to cover what it is, how it works, what people expected it to be, and why we think it failed. We'll later show you what is eBPF and how we think eBPF is reviving the field of runtime application security. It's important to say we will have time for questions in the end, so if you have questions, please write them down and we'll get to them later. So the need to protect applications is not new, and thanks for ChatGPT for this amazing, amazing image. So for centuries or decades maybe, developers and security experts have sought ways to shield software against threats. Traditionally, application security have been implemented by focusing mainly on the left side of the SDLC, that is using static tools such as SCA, SAST, code reviews, and so on to improve the security posture of the application. While other real-time tools, such as firewall or API protection tools, do offer some protection in runtime, they usually lack the crucial application context that is needed to protect against many threats. And recent events, such as Log4Shell, Spring4Shell, the XZ backdoor, and in general the vast amount of organizations that are facing attacks, proves that traditional security tools are simply not enough to block or detect application threats. You ask yourself why? So it's because these attacks, they happen only in the runtime, and they require proper application context to detect, and therefore are usually not detected by existing tools. So to address these issues, a new category of security tools have emerged and was quickly adopted by CISOs all over the world. So it was first introduced by Gartner in 2012. RASP, which stands for Runtime Application Self Protection, is a runtime application security solution that uses application-level software instrumentation methods to wrap the application's code in order to enhance its security in production. RASP was the first solution that emerged in the market that attempted to provide a solution for application attacks in production. And spoiler, it's working, but it's far from perfect. But before we can dive into why, let us introduce RASP, what it is, how it works, and why we think it failed. So we already know what RASP is trying to solve, but how does it do it? So RASP tools work by adding runtime checks and validations to your application in strategic places. It operates by utilizing strategies such as software instrumentation, additional function decorators, or adding dependencies during the build time to inject security tests into your functions. During execution, RASP evaluates inputs and outputs of the application in the application's context and tries to determine whether an attack is taking place. So with some help from ChatGPT, I want to show you an example of how a RASP rule might look like for detecting SQL injections. I hope you can see something. But what you see here in this image is some code that receives an SQL query as an input and tries to identify whether an SQL injection might take place. So it is looking for some SQL-specific keywords. And these keywords are usually something that attackers will try to insert when trying to assess the exploitability of SQL injections. So the RASP agent later hooks into the SQL library that you use in order to query your database, and it inserts these tests before running the actual query. So if it sees something that is odd in this context, it can just block or at least detect these attacks. The RASP agent can later be injected into running processes. This is what is called instrumentation. So this is an example of how you inject using Java agent. You can inject into Java code, and you can use LD preload to inject code into your Go application. But note that not all languages support this way of injecting code into them, which adds a bit more complexity into deploying such solutions. So since ChatGPT tends to lie, I've also included a real example too. This is taken from OpenRASP by Baidu. But as you can see from the function name, do real check without request, real code tends to get really messy, so we will stick with the ChatGPT from now on. Okay, so another way of implementing RASP is by adding these function decorators. So this is a Java function that is doing pretty much the same thing as we saw in the last example. It is defining a decorator, and then to use it in your code, instead of injecting the RASP agent into your code, you just need to wrap all the query methods that you use to query the database with this detect SQL injection decorator. And then it will also run the checks before running the actual query, and you can decide to block them or do whatever you like. So in general, RASP is meant to protect the application and detect the exploitation of vulnerabilities. It is not trying to detect attackers that are already inside your production environment. It is usually, this is usually handled by workload protection tools that focus on the host and are also typically used in container security. And also note that each framework, as we've just seen, have to have its own rules in order to have full coverage. So while RASP can be efficient in detecting some application-based attacks, it suffers from some major pitfalls. Let's talk about why we think it failed. So as a security solution designed and implemented in the past decade, RASP suffers from some major pitfalls which have led security experts to consider it as an added layer of protection rather than a must-have security solution. Friction, unpredictable impacts on performance and stability, and deployment challenges are just a few of its problems. But the main issue is it doesn't scale. Let's see why. So first and most importantly, stability. Integrating into applications level code is a non-trivial and expensive undertaking that can potentially lead to stability and performance issues. This is because due to the way RASP instruments your application, if your RASP tool happens to have a bug and crash, your whole application crashes. And believe it or not, bugs exist, and applications do crash, even security tools. And of course, you cannot take a bet on production server stability. Any resulting downtime can have an impact on SLAs, causing revenue losses and damaging the company's reputation and market position. The second reason is the added friction. So the GIF here is actually how you add the RASP agent into your build file. So as we've seen, many RASP tools require the developer's interaction in order to integrate with them when the code or build changes are needed. And the thing is, developers are usually not measured for the security of their applications, sadly, but that's what AppSec are for. Developers are being measured for delivering features as quick as possible. They simply lack the time and motivation to invest in the cumbersome process of integrating security tools, which can be very frustrating. Like, why integrate a tool that only makes my product break? And in addition, the RASP approach covers only specific functions that are considered fragile or vulnerable. In most implementations, RASP offers security solely for the code that has been specifically wrapped by the user, as we've seen with the decorators example, thus leaving third-party components with no protection at all. And last but not least, deploying RASP tools in production is operationally challenging. It's essential to acknowledge that due to the methods RASP is implemented with, RASP requires distinct deployment and customization for each individual application. And also, when new threats emerge, updating RASP tools can be very challenging due to the complexity of the implementation and deployment, which adds another layer of risk of instability. In other words, it's very difficult to re-instrument an application when you update the RASP tool without crashing or restarting it. And indeed, as you can see from this Gartner Hype Cycle report for application security in 2019, RASP continued to prosper and almost reach maturity. It's marked with red. But then in the report from last year, it suddenly disappeared. So it's kind of small, but trust me, it's not there. And just to check, raise your hand if you have a RASP tool running in your production environment right now. No one. But the fact that runtime self-protection is dead doesn't mean that there is no need for runtime protection at all. The market still demands a scalable runtime security product. We just need to find a better technology. This technology needs to be seamless and frictionless, ensuring that it does not disrupt the performance of the application and does not introduce developer friction. It should provide comprehensive attack coverage, monitoring the entire host rather than just the application. It should be easy to deploy and maintain, but most importantly, it should be stable. And we believe that eBPF can answer those needs. So let me hand the speak to Avi to present how eBPF is answering these challenges. Avi?
Thank you, Guy. Thank you for being so awesome. Now, let's talk about the role of eBPF in today's AppSec. eBPF is much more than just a buzzword. Let's begin with a high-level overview of eBPF's strength. I know some of you might be familiar with, but I'll go over them quickly. eBPF is known as Extended Berkeley Packet Filter, is a groundbreaking technology in the Linux kernel that allows us to run user space programs in the kernel in a very, very safe way. BPF programs are actually compiled to BPF code, which you might be familiar with if you ever used IP tables, for example. So you've used the BPF virtual machine. And just like IP tables, it does not require reboot to apply changes to your program. You can do it without restarting the server, unlike kernel modules, which is a big difference. And most importantly, it is safe by design. And let's understand what it means. The eBPF subsystem uses something called the eBPF verifier. It basically asserts that our code is safe from infinite loops, invalid memory access, and that it basically does not hang or block and might end up crashing an application. So it basically asserts that it won't crash the system. Why should I use eBPF besides? So it's very, very dynamic. All you need is Linux. You know, maybe 7 or 8 years ago you wouldn't have said that, but today it's not the case. eBPF is almost on any Linux out there. So you can just pop SSH to any given machine, hook a specific place inside the operating system and gain visibility like a zoom in where you need it the most. Without any further installation, without risking your application ending up crashing. And your application, most of all, can be already running. You don't need to restart it in any way. And eBPF is very efficient besides that. Thanks to the just-in-time compiler and lack of context switches, eBPF results in very, very low latency. And we all love that, but eBPF is actually battle-tested in production by large companies such as Google, Facebook. Facebook is actually, Meta have been one of the early adopters of eBPF, and they've been writing eBPF programs since 2017. And Netflix, who uses it for performance engineering. You might know Brendan Gregg, which I'll mention also later. He did amazing stuff with BPF at Netflix, and the list goes on, believe me. eBPF probes allows us to support many different kinds of applications. So eBPF is very versatile. And if you don't believe me, there are 120,000 hooks that you can hook inside the kernel and gain visibility just like that through the BPF program. 120,000, that's an amazing number. That's basically every function in the Linux kernel can be hooked. You can access system calls, I/O events, scheduling events, TCP, UDP, networking events, and even context switches, and much, much more. And until now, it was used only for observability and performance engineering, sometimes for networking, but not really for security. So I'm going to focus on security tools soon. And first, let's understand what an eBPF program can access. So unlike before, eBPF allows us to hook all of these probes that I've shown before. The most interesting ones are trace points, which are lightning fast. They are integrated inside the Linux kernel already. And these are just designated hooks that can be probed by the BPF program. And as I said, are considered the fastest among all of the probes. And get this, attackers cannot avoid doing system calls. This is why many security tools look at the system calls that your application is doing. And remember that not all system calls were born equal. So it basically tells us what the application is doing, and just like that, and it's already being done, you can look at the syscall enter or exit event of any syscall in the Linux kernel. And besides syscall, there is also USDT. USDT allows us to insert designated hooks inside the program that we run. Let's say if I have a Python interpreter, so it allows me to insert specific hooks inside the Python interpreter, such as function entry, which you can see in here. It's taken from an open source that I've written that we'll see soon. And these are two first kinds of probes. The first program will simply kill a Python process if it uses os.system command. It's just like 3 or 4 lines of code, which I think is amazing. And there are much more than just these 2 examples. So it is used for networking purposes. Actually, Cloudflare is one of the pioneers, and they've used XDP, Express Data Path, to mitigate and draw packets early before they propagate to the Linux network stack and reach IP tables, which consumes much more CPU than dropping them early, even before they reach the network stack of Linux. It allows us to scale maybe from 1 million packets a second to 5 or 10 million packets a second, which is amazing. Remember that eBPF is only the building block, and it takes much more than just these hooks to create a program that's actually helpful. And there are some barriers to entry, because eBPF focuses solely on the interfaces with the operating system. And if you use it right, that it can allow us to do what's considered previously impossible without impacting the application's integrity in any way. But as I said, there are barriers to entry. You need to be proficient in Linux and understand the eBPF ecosystem. And it does not take just 1 day. It's really hard to create code that does not slow down the application. So writing production-grade logic is not easy outside of the box, and you need to know what you're doing. And the ecosystem is limited. So it was mostly used for performance, as I said. And if we look at strace, for example, which is, by the way, is not suitable for production environments, it has an open bug for at least 10 years in the man page of strace that simply says a trace process runs slowly. So you cannot do it and apply it on a production environment. At least I wouldn't have. And it leads me to this point. Performance tools are not security tools. If you know Brandon Gregg, which is one of our gurus in eBPF, it's a famous saying that I really love. And just to prove it, I don't know, this is the proof, right? strace is not suitable for production, and the tools that we use today are mostly built around visibility and not around security. So what is the connection between eBPF and security, and who does it already? So it is a trend. We see large companies and small startups implement security products that are based on eBPF. If we look at Falco by Sysdig, there's Tetragon by Cilium, and there's Tracy by Aqua Security. And it's just a few. There is a trend, and there's a trend for a reason. It enables us also to do things like KRSI, which integrates LSM, Linux security models, with eBPF for enhanced security hooks. And we can actually control and block attacks if we detect them using eBPF hooks in real time. And also there's memory access, which is very important. As you can see, the program in the bottom figure allows us to catch out-of-memory kills just outside the box. So it uses a designated kernel probe, and it allows us to do that. We can also count the syscalls, which is not that interesting. You can count the network packets, and you can even take a look on the Firefox HTTP row transport after it was decrypted and peeled from the TLS. So all of this is just a tiny example, and it's possible. Let's say in this example, we can also create a web application firewall that is completely eBPF-based, just like the first firewall, which was BPF-based. Now, with these examples in mind, I want to look at an open source that I've created. I called it Secimport, and it's a library-level dynamic eBPF sandbox. It enables us to confine specific models in your code, in the Python process, by the library or function level in real time. Now, why? Because a library derives the privileges of the process that it's running under, right? I think it sucks. If we look at log4shell, for example, so a logging library was abused to bind the session and open a server, and it should never do it, right? It's just a logging library. It should only write logs. It should never access the network. The same can be said on XZ. It should only decompress and compress data, and it should never run arbitrary system commands. We'll get to that soon. But in 2017, eBPF was not as mature, and it was not present on any Linux machine, but today it's not the case. And 7 years later, eBPF is literally everywhere, and almost everybody uses it. So I wrote this simple open source that can utilize eBPF to confine libraries in your code. And it uses USDT and trace points, which I've mentioned earlier. And you can trace and then enforce the syscall of a given application to the module level in Python or to the package level in Python without risking your code of ever running it. So it acts like a man in the middle between the Python process and the Linux kernel. And it's pretty interesting because it does make one-day attacks less of an issue, because you know that if one would have exploited the one-day attack, so it would not be ended running. So it literally blocks the attacks, and let's see how it works. So this is an example profile. You can see, I hope you can see it, by the way, but there are 3 different models. Each of them has different syscall that I am allowing it to run. So it's composed of 3 simple commands. The first command is trace, which simply traces a running process or a new terminal, and records all the syscall for every module in the code. And then it results in this policy file. Then the Secimport build command compiles this policy to BPF code, and the run command allows us to apply and enforce the security on a running process or a new one. So in this example, I've created a FastAPI application that simply has a backdoor in it. I triggered this backdoor, which is known only to the attacker for the sake of the example. And just in time, it violated my policy, which resulted in SIG-stop, who stopped the application. And as you can see, the page did not return, the server did not return anything to the attacker, sorry. And just to make sure you got it, we ran the exploit in real time. The sandbox detected the anomalous behavior because the library behavior changed in the syscall level. And then we send a SIG-stop to the process, and we can just access the memory of the process without killing it. But of course, you can also kill the process. And this is basically the notion of Secimport. Now let's jump to the XZ use case. Secimport, by design, should be able to detect XZ, but I built it for Python, of course. It was a POC for the notion of being able to detect behaviors that's changing in libraries in a given environment. And of course, Secimport is not a production-grade solution. It's merely a POC, but it's working and it's amazing. And spoiler alert, we have detected the exploitation of XZ, and let's see how exactly. So which tool can detect 0 days? I mean, theoretically none, right? If we look at XZ, the attack resulted in a poisoned artifact in GitHub. So The attackers actually managed to propagate the backdoor all the way to almost LTS versions of Ubuntu and Debian, but luckily enough, it was caught on time. And when XZ, the world has literally gone crazy. I mean, the backdoor caught us with our pants down, and I'm feeling very lucky. And I'm feeling lucky and unlucky at the same time. And I'm just thankful they not propagate all the way to Ubuntu LTS, and that was discovered in time. And all of this is just thanks to a curious developer that noticed half-a-second overhead in his SSH sessions. And I'm mostly concerned about what we don't know yet, and what's only waiting to be exploited. Almost all the companies that build detection tools or visibility tools around the world claim they can detect and remediate XZ somehow and prevent it, but they did not provide any evidence of doing so. And I think detecting XZ is not as hard as you think. Here's the secret. The application context is all you need. SSHD is composed of many different libraries, right? Among them is XZ. We understand that SSH should call libc's system command, which can run arbitrary code, but inside SSHD, XZ should never call this flow. It should never call the system command, not in any real world use case at least. It is that simple. How many of you were impacted by XZ? Okay, try to reminisce how your organization approached this incident, how long did it take to resolve it, and why does it always happen during family weekends and family vacation? Am I right or what? Like, it always catches us, as I said, with our pants down, which is exactly why I've originally developed and published Secimport. And how did we detect it? So typical organizations usually rely on CVE for vulnerability management, but there is a problem with CVEs. They lack critical application context, and they can also only be applied retrospectively. So traditional tools would require a specific rule or specific CVE in order to detect XZ library vulnerability. But we were able to detect it without any special rule or CVE and based only on the library behavior. Imagine Secimport, but wrapped as a scalable production-grade product and fully autonomous. And at Oligo, we've built a vast DB of runtime profiles for each and every library out there that's widely known, such as XZ and SSHD. We managed to replicate the attack provided by the samples by Anthony Wims on GitHub. We triggered the backdoor and expected the backdoor to be detected by the eBPF sensor. And as expected, our incident was created automatically, and our eBPF approach, which focuses on the library behavior rather than a CVE, caught it just in time. And remember that XZ should only decompress data. It should never run arbitrary system commands, even if SSHD is capable of doing so. We don't have time for the video, but there's a video on our website if you want to watch it. And let me conclude. So we've seen in these examples that eBPF can be used to identify and block application-level exploits in real time, which cannot be detected in CI/CD or at build time. Secimport was just a POC for this behavior-based sandbox. And in Oligo, we've built a scalable runtime security solution that is completely production-grade and detects application-level exploits in real time. It can even detect 0 days, as I said. And all of this is done in a much more efficient way, and first of all, stable way, unlike before. And thank you very much for your time. Now we have some time for questions.
Hey, thank you for the great talk. So one of the last slides showed you that you are detecting the system function call, which is actually a libc library call. Now, on the other hand, we talked about before that eBPF is good at detecting system calls, not the system function, but the system calls. So I see that there is a gap here.
Yeah, just to make it more simple, we called it the system function, but it's actually fork and then execv, so this is what we detect.
So I have a follow-up question about that, because one of the most problematic part of this backdoor was, from a detection point of view, was actually that the fork and execv is actually what an SSHD server is designed to do. So from a detection point of view, from someone like you who are sitting on the kernel side and seeing only, you know, fork and execv, it is the normal behavior of the application.
Okay, so this is exactly what is special on this approach, because this is what what Avi said, that SSHD is supposed to have like forks and execs, but how you can detect inside what happens. So what we did, we added the application context, so we basically know for each system call where it originated inside the application. Okay, so you can differentiate if it came from SSHD and one of the functions that are really supposed to do fork and execs. But when you see that XZ is doing that, you know that XZ was never allowed to do such a thing. So this is the essence of the approach.
Very nice. Thank you very much.
Thank you.
Do we have any more questions at this time? You'll be able to approach the speakers during the course of the day, and as mentioned, you'll be able to find information on their website, and in the future everything today will be up on the website related to today's conference. Anybody else? No? In which case, Guy, Avi, thank you both very much.
Thank you very much.